Welcome to the sixth presentation in the sixth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the sixth webinar of our sixth series, which we'll continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the sixth series will be distributed through the IAS mailing list, Twitter feed, and LinkedIn page. Today's webinar will be given by Dr. Enzo Mangano at the University of Edinburgh in Scotland. It is also part of our special IAS webinar series titled Diffusion and Nanoporous Materials, Guidelines for Measuring and Reporting, focusing on the recent IUPAC technical report, Diffusion and Nanoporous Materials with special consideration of the measurement of determining parameters. I'm Nicholas Wilkins at Svante Technologies Incorporated in Canada. Today's webinar will be moderated by David Donacci at Imperial College London in the UK. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you have not already. Our dues are minimal, only $20 per year, but support the publication of our flagship journal, Adsorption, contribute to travel grants, and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS-supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @intadsots for future updates regarding IAS events, webinars, and information about scientific meetings. We have also started an IAS LinkedIn group, which could be found after searching for the International Adsorption Society. Please help us expand our YouTube channel by liking this video and subscribing. We would like to remind the attendees of the 15th Fundamentals of Adsorption Conference that is being held this year in Porto, Portugal, between May 18th and 23rd, about a month from today. Additional information can be found at the URL given on the slide. We look forward to seeing everyone there later this year. I'll now hand it over to David Donacci, who will moderate the YouTube Q&A.
Thank you, Nick. It is my pleasure to welcome Dr. Enzo Mangano to today's session. Dr. Enzo Mangano is a senior lecturer in chemical engineering at the University of Edinburgh in Scotland, where he focuses his research on the equilibrium and kinetic characterization of novel nanoporous materials for gas separation, for gas adsorption. During his career, he has worked on experimental methods to measure adsorption equilibria and kinetics on a wide range of adsorbents for carbon capture and other separation processes. More recently, he has developed a novel adsorption differential volumetric apparatus, ADVA, for highly accurate measurements of equilibria and kinetics at high pressure using small sample masses. His current research focus is on the measurement of high-pressure adsorption on porous materials for a number of applications, including gas storage, transport, and pressure swing adsorption. Dr. Mangano was awarded the 2016 Italy Made Me Award from the Italian UK Embassy as Young Italian Researcher of the Year in Scotland, and he has published 47 publications in the field of adsorption with over 4,500 citations. During the webinar, questions can be submitted to the speaker in the YouTube live chat, and I will moderate them at the end of the presentation. And with that, I welcome Dr. Enzo Mangano again and pass over the presentation to them. Thank you, Enzo.
Thank you. I'll start sharing. It should be on, right? Should be able to
Yes,
see it.
we're able to see, yes.
And you're able to see me as well.
Exactly.
Perfect. Okay, so stop. Start. All right, so welcome everyone, and I would like to thank the International Adsorption Society for the opportunity to have this webinar online on YouTube to discuss about volumetric and gravimetric techniques and their use for measurements of mass transport kinetics in porous materials. The outline of my presentation will go through a number of items. We'll go through the configuration of gravimetric and volumetric systems, an overview of the common practices found in recent literature work. We'll talk about signal conversion, bed effects, the Ruthven number, and finally, we will conclude with IUPAC recommendations. I'll also invite the audience to check our 2020 webinar on the first series of the webinar from the International Adsorption Society on macroscopic measurements, the one that Stefan and I gave. There you will find some details that I will probably go very superficially on today, because obviously there is this extra resource to check. Obviously, this webinar is part of the series on the IUPAC initiative, and I would like to start thanking Professor Karger for the effort, the immense effort of putting together this document, which I hope is will be one of the most valuable resources for our community. Is the IUPAC technical report on diffusion in nanoporous materials. A lot of people worked on it, and it's an effort that has taken a number of years. So it should be the resource that anyone working in kinetics or willing to work in kinetics should check first. And then I will direct you also to the topical issues that are present in the Journal of Adsorption, where you will find the 21 articles where the details of each techniques are explained in much more details. So obviously, starting point, the technical report, but then also check the topical issue on diffusion nanoporous material was published in 2021. One of the papers that are included in that topical issues is also one of the paper I will discuss in my presentation that will I consider to be the backbone of my presentation. It's the review on common practices in gravimetric and volumetric technique that we published in 2020. Many of you probably recall my work in a lot of flow system, and particularly on the zero-length column, and our lab has a lot of them. But we also have a number of gravimetric and volumetric techniques. Gravimetric techniques include the systems that are in flow and systems that work at high pressure, not in flow, like the Xemix microbalance. And as was specified in the introduction, we also work with volumetric techniques. We have commercial systems, single branch, but we also design our own differential volumetric apparatus that you see in the pictures here. We have 3 at the moment that go from low pressure to high pressure, so from 1 bar to 60 to 70 bar. So we'll go through also a little bit of the details of this system as well as we go along with the presentation. We start first with the configuration of gravimetric systems. Gravimetric systems, from the point of view of the technique, is a very straightforward technique. What we are measuring is the mass of the sample as adsorption takes place. And the mass balance, the way in which this is calculated is through a balance of forces. And there are two main configurations for this system. They can be directly connected or magnetically coupled. And in most systems, they are in an asymmetric configuration, like the one you see in the picture on the right, or in a symmetric configuration, like the one on the left. For the equilibrium measurements, for which these systems are normally designed, so most of these systems are normally commercial systems designed for equilibrium, not for kinetics. The important, the final correction for the buoyancy is only important, but for kinetics, sometimes you need to also take account and model the forces that apply during the transient uptake. Another important differentiation between the gravimetric systems is also the way in which the pressure step is implemented in the system. Normally, this one can be done using a large volume of gas via valve and a restriction, or you can have a mass flow controller and a pressure controller and a pressure regulator. And it can be with or without a carrier gas. This obviously is important because based on the way in which the pressure step, the concentration step is applied, also the way in which you interpret the data and analyze the data changes. So we'll go through some of the most simple example of the gravimetric system. First configuration is the configuration which the pressure step is applied by having a mass flow controller to feed extra gas inside the chamber, and then having a pressure regulator to reach the new set point. The schematic diagram here shows how this normally happens. So the flow increases, the pressure increases, and this increase and transition to the new set point is normally on the range of few minutes, because obviously with a balance, with a macro balance, you want to avoid abrupt changes to essentially affect the stability of the balance. The experiment is normally in flow, and you use a pure gas for this type of pure absorbing gas for this type of measurements. In another configuration, you will have a system in flow where you have a carrier gas and an adsorbate that mix and generate the concentration, the partial pressure required. And in this case, the total pressure remains constant, and the step change in concentration is done by essentially manipulating the mass flow controllers of the adsorbate and the carrier in order to achieve a higher pressure, partial pressure of the component of interest. The transition to the new set point obviously depends on the flow rate you use and the volume of the system. In balances, normally the flow rate don't go up very abruptly, again, for the stability of the balance. Finally, there is another version of gravimetric, which is more a volumetric gravimetric system, where the change in pressure of the adsorbate, of the pure adsorbate, is done using a dosing volume, generally a large chamber, connected to a valve, via a valve to the balance. You open the valve, normally there is also a restriction to, again, limit the effect of instability of the balance. And the pressure is led to a new value of pressure, to a new set point. And in this case, depending on obviously the size of the dosing volume, the pressure can be essentially very large compared to the mass of the sample, the mass, the adsorbed amount. Or if the volumes are more small and more comparable to the amount absorbed, you may have actually that this approximation of the constant pressure is not valid, and it's more like a conventional volumetric system where the pressure changes during the experiment. So what's the difference? The difference between the three systems is essentially that the model that you need to represent your system changes depending on the way in which the pressure and the concentration step is applied. In the first case, we saw that the system can be modeled and understood as a system where the pressure is constant. In the case in which you have a flow system, this becomes essentially a flow system, so it can be represented by the model of a CSTR in flow, where the flow rate is relatively large compared to the amount of sample. So in this case, is more similar to a zero-length column, where the main difference with the zero-length column is that now the monitored variable is directly the amount absorbed via the weight of the sample. Obviously, I won't go into the details of this. All the recommendations that apply to flow system will be covered by Stefan in the next webinar. The last, obviously, the last configuration is more similar to a volumetric system. And as I mentioned before, the general assumption is that the pressure, the general case is that the pressure changes during the experiment, reaching a new set point the moment you open the valve and the adsorption starts. In the simplest model that represents the ideal step for standard change in composition is given by the equation above in this slide. And what I'm trying to explain with this is that in many cases, as I mentioned before, the transition between the step, the application of the pressure step and what actually is seen by the adsorbent may take a few minutes. So this is because the volume of the system and the fact that you need to implement measures to prevent the instability of the balance require that the flow change and the pressure change inside the balance is gradual. So this transition can take up to 1 or 2 minutes. So this means that if you need to pay attention to the amount, so to the time, to the diffusion time that you're trying to measure. What you want is that the diffusion time that you try to measure with the gravimetric systems is about 10 times the time required by the kinetics of the system to establish the pressure step. Why this is important? Because if you apply the model, the simplest model where you have the perfect change in pressure, you can see that 90% of the response is essentially seen at 0.2 times the diffusion times. This means that if your diffusion times is 100 seconds, your 90% of the response would be in 20 seconds. This means that in order for you to see it, the response of your balance needs to be a lot quicker than that. So this means that if the response of the balance to the change in pressure is on the order of 1 or 2 minutes, you will be able to see diffusion times in the order of few minutes, 10 minutes, 5 minutes, but not faster, because then it will be most of the information, the kinetic information, will be essentially masked by the increment of pressure of the system. One example is in the two plots, experimental plots shown in this slides. On the left, you have an ethylene adsorption in 5-8 zeolite. On the right is ethylene again on carbon molecular sieve. So a fast system and a slow system. In the plot on the right, on the plot on the left, what you see is that you see an initial linear increase of the pressure of the amount absorbed, and then some fluctuation at the top. This is because the system, as you can see, reaches the equilibration in about 1 minute, and what you're seeing here, especially the linear increment in the amount absorbed, is the actual pressure control of the system that is trying to reach the new set point of the pressure, with the oscillation of the essentially the PID controller of the pressure controller. This means that all the information that is related to the kinetics of the adsorption is completely lost, because it's way faster than the adjustment essentially of the pressure of the system. On the left, on the right instead, what you see is a slow system. So now if you look at the x-axis, we are going from a few minutes to thousands of minutes. So now here, you actually have a system that is can be measured very accurately for the diffusion times. The process time, i.e. the time that the system requires to reach the pressure required is on the order of a minute, as you see in the plots on the left. So obviously it's completely negligible compared to the process time of adsorption, essentially. So in this case, assuming, for example, the perfect step would be a reasonable application for a slow system like ethylene in carbomolecular sieves. So it is important to understand how the system works in order to understand which assumption I can make in my model and if the assumptions that I make are reasonable for the system I'm trying to measure. Following a similar approach, we now look at the configuration for volumetric systems. Volumetric systems are much simpler in design, and they normally involve a dosing volume with a pressure transmitter, a valve in between, and an uptake volume where the sample is placed. The principle of operation is really simple. A known amount of gas is dosed in the dosing cell. The valve is opened, and put in contact, the gas essentially flows to the uptake cell, and the pressure is monitored while the adsorption takes place. In this case, compared to the balance, we are not measuring directly the amount absorbed. The amount absorbed is calculated via essentially the pressure and the calibrated volumes and the mass of the sample. They generally offer a faster response compared to the volumetric, to the gravimetric, and you need, especially if you work at temperature a lot different from the ambient temperature, you need the definition of the temperature zones as well. Very rarely you may find also configuration with the pressure readout on the uptake cell, but for kinetic measurements, these ones are generally not required, and the drawback in that is that you may have an increase of the volume of the system that you want to keep as small as possible in order to minimize the response of the system and have more accuracy in the response. As I mentioned in the original, in the start of the presentation, we design volumetric systems as well. And the system we design are differential volumetric apparatus. So ADVA stays for adsorption differential volumetric apparatus. It's the same concept of a volumetric system, but this time you have two symmetrical branches connected by a differential pressure transducer. The main advantage of having a differential pressure transducer in between two identical branches is that you increase the accuracy and the resolution throughout the entire experiments. This is very useful for equilibrium, as you essentially rely on the accuracy of your differential pressure throughout the entire pressure range. But it's also very useful for kinetics, because most of the kinetic information would be in the last 10 to 1% of the signal. So this configuration offers a high signal to noise ratio, which allows essentially to have an extra order of magnitude of resolution over the tail of the kinetic information. The system obviously is designed with very small volume, so allows very fast kinetics to be recorded, and we'll see how quickly this system go in the next few slides. Okay, so general recommendation for gravimetric and volumetric system, which I think I went through the general introduction of the systems, is that these systems are generally either commercially, you can find either commercial system or you can build your own, especially for volumetric, but most of the systems are generally designed for equilibrium. They can be used for kinetics, but you need to have an extra level of care in order to make sure that your system can actually work and be able to measure accurately the mass transport. There are limitations on the amount of sample that you can put in each system, and also the configuration of the sample that you can bury inside the system. This means that sometimes, for example, the sample, if you use a monolith, won't be able to load it in some of the optic cells. You can go small in sample mass, but remember, for equilibrium, you may want to go higher. So obviously, there is a trade-off between the amount of sample that you can use and the resolution of your system. Gravimetric systems are generally not very suitable to measure very fast kinetics. Due to the design to constraints, the way the flow is designed around the cell, the way the volumes are designed, and so on. Most of the systems are static, so they are prone to heat effects. And this is a theme for both these techniques of gravimetric and volumetric, and non-isothermality can be addressed, of course, but by increasing the thermal mass, reducing the absorption depth, reducing the amount of sample. But you will see not always is possible to eliminate it entirely. So sometimes it simply is impossible to eliminate. Fast systems are likely to be non-isothermal, even when you apply the best practices, and I'll show some examples of that. And obviously, you need to perform the essential experimental check in order to make sure that the assumption that you make in your model actually reflect what the real system is doing. While these aspects seem very obvious, by searching on the most recent publication, not always this recommendation is followed, especially when you look for publication that report diffusion coefficient. So on my next chapter of this presentation, I'll go through some of the findings that we reported in our review of common practices. What was the objective? The objective of the work was essentially to review the practices followed in the use of volumetric and gravimetric systems to measure mass transport kinetics. And we followed the methodology. The methodology was quite simple. So we searched for all the papers using gravimetric and volumetric techniques to measure kinetics, starting from 2020, which was the year we were drafting the manuscript, and starting from the most recent papers and going back in time. For each of the papers, we started collecting the metrics of interest for our review, and we stopped the essentially adding paper when the metrics we were observing were not changing anymore with adding further papers. So in total, we reviewed 108 papers. We split them. Obviously, we make sure that the same amount of paper were used for gravimetric and volumetric system, and all the papers that we looked at were published between the year 2000 and 2020. Obviously, the list is not meant to be exhaustive, and it shouldn't be like so. And I would like to point out that there are a lot of very valuable publications. A lot of the work done in the 70s, in the 80s, in the early 90s. Followed very well some of the recommendations that I will point out. So please go and look also to more dated papers, because they are very valuable. The models and the experimental checks that have been done at the time are essentially in line with most of the things that we recommend in the IUPAC report. All right, so the first simple overview of the gravimetric and volumetric systems. Majority of the gravimetric system is commercial. This is due essentially to the complexity of building a balance compared to the complexity of designing and building a volumetric system, where the split between purpose-built and commercial system is 50-50 almost. Majority of the system, as I mentioned, are designed for equilibrium measurements. The model used, vast majority of the system, both in gravimetric and volumetric system, assumes an isothermal model. A small proportion uses a non-isothermal model, and then very few use some empirical models. In many cases, the response, as you will see, is likely to be non-isothermal, but many of the papers do not actually check for the non-isothermality. So it's important that once the assumptions are made, the models are checked, and if so, the right model should be used. So non-isothermal if you see non-isothermality, isothermal if you see no sign of heat effects. And then obviously, what is another thing that is a bit concerning, that there are a consistent and significant number of papers that on volumetric systems, on the volumetric technique, that assumes a constant pressure model when clearly for volumetric system, the pressure changes with the absorption. Linearity and isothermality. Here, what is important to look is essentially people and research that confirms does the actual checks to confirm isotherm linearity by doing adsorption and desorption. You need to look at the y-axis. We are talking about 77 paper out of 90, so less than 10% of the papers considered actually do the configuration change of the sample and the linearity confirmation by doing the adsorption and desorption. And this is something that should be done as a default check for any of the experiments that are done both in gravimetric and volumetric system. Why the effects are really important? Because sometimes, as I'm showing this example here, you can do a lot to actually implement and avoid, do implementation to avoid the occurrence of heat effects. But in many cases, there is no way you can actually get rid of them entirely. So this is an example where a microbalance is set up with a number of trays, where each tray has essentially a monolayer of zeolites. So the sample is distributed for optimal heat exchange. Very small sample mass is used in each tray, and the pressure steps are very limited, 1.9 to 4.5 millibar. And even with that, the response has some heat effects. And for the case with Britain, the system is completely heat limited. What you see on the plot is that also the first data points is essentially the first data point is essentially 80% of the relative uptake. So a lot of the response is essentially missing just because of the acquisition time and the response of the system itself. Pressure step, as I mentioned before, there are different ways in which the pressure step can be applied, especially when we talk about gravimetric. But what is important is to report how big is the pressure step or the concentration step. In many publications, this is specified. This is true for the gravimetric, and about 50% of the volumetric systems specify how big is the pressure step. In some cases, the amount of the pressure step is not specified. In any case, small pressure step should be performed at all time, and the check with variable pressure step should be done also to ensure that the system is under linear isothermal condition, so the linear isothermal condition. And if not, obviously, the appropriate model should be used. So the nonlinear model, if you're using a big pressure step, should be used in this case. An essential check, very easy to do, that can be done in any of the techniques is to run the adsorption and the desorption at the same pressure step. Sample mass of the sample, obviously, as I mentioned before, it's always preferable to work with as little sample mass as possible. This is because, obviously, for kinetics, you want to avoid incurring into bad effects and heat effects. So the smaller the mass, the better. But as I mentioned, most of the systems are designed for equilibrium. So obviously, in the instructions and for equilibrium purposes, obviously, you want to use as much sample as possible. For kinetics, obviously, you want to go the opposite way, use small sample mass. But what is worrying in the findings from our review is that there is a large proportion of the paper that they don't even mention how much the sample they used in their experiments. Obviously, recommendation that you will find across my presentation and the IUPAC report say that on top of using sample mass that is limited as possible, you also should check by changing the sample mass for heat effects and external mass transfer resistance. So an additional check with different sample mass is always suggested. Last metrics was about the signal reported. When possible, and it's always suggested to do so, is to present both the raw signal and the converted signal. As you can see here, very few papers report the raw signal. a considerable amount reported a converted signal with or without the fitting. Obviously, what you want ideally is the raw signal, you want the converted signal, and also the model that goes through the data, because there are cases in which there is no model presented and still a diffusion time is reported. So obviously, it's important that all the signals that are relevant are reported to allow everybody to understand the way in which the diffusion time was determined. I'll now go into a little bit of discussion regarding the converter signal, because obviously the way you convert the signal is also important for understanding what are the resistances involved, and there are different ways in which you can do that, and it's important to understand which way is best to convert the signal and report the signal to have the most of your kinetic information. For this, I will use the example of a volumetric system where essentially as I mentioned, is an indirect measurement, so you have to convert the signal into a quantity that you can then analyze using a kinetic model. The way the system works is depicted here in the raw pressure signal plot, where you see that initially the uptake cell is at an equilibrium pressure. The pressure in the dosing cell is then, with the valve closed, obviously increased to a new value, which is P0D. And then once the absorption experiment starts, you open the valve in between the two volumes and you allow the system to equilibrate to P infinity. Now, if you assume that the equilibration of the pressure between the two volumes is instantaneous, you essentially have that the case where the valve is infinitely fast. Okay, so in this case, what is generally done is that it's assumed that the two sides are equilibrious first, and then the absorption starts. And the initial P0 is calculated using the relationship here. And the pressure data are then converted into amount absorbed using what is called the fractional uptake, which is essentially the conversion between the pressure difference and the amount absorbed. And this is done in about 85% of the 90 papers considered for the volumetric. This assumption of the infinitely fast flow through the valve is valid, obviously, when the valve is a lot faster than the diffusion time that you're trying to measure. What's the drawback of such approach is that if your system is instead fast, you're losing part of the information, which is in the initial instance after you open the valve. This is an example that we reported in a collaboration with Air Liquide, where we looked essentially at the absorption of nitrogen on lithium LSX beads. Here, the software, the commercial software of a commercial volumetric system reports the transient uptake, as well as a model that goes through the data. The way in which the model is calculated by the software is that the kinetic model goes through the point at 50% of the uptake, and chooses the model, so the transport mechanism that more closely matches the data. In this case, what you see is that the model chooses a surface barrier model as it sees better fit with the experimental data, but it loses completely the initial instance after opening the valve. A better way of converting the signal for volumetric system is instead to use the reduced pressure. In this case, you make no assumption of the initial equilibration of the volumes between the volumes of the dosing cell and the uptake cell, and use directly the information that you have from your pressure signals. So in this case, the reduced pressure uses the P infinity at equilibrium, the P signal during the variation, during the absorption, during the time that the absorption takes place, and the P0 before opening the valve, so the P0 in the dosing cell. In this case, there is no assumption, and you can clearly identify if there is a valve effect and if you should consider it in your analysis or not. How the reduced pressure plot looks like, this is in this slide here, where we show essentially the reduced pressure plot obtained from the simple isothermal model from Stefano in 1998. Here you can see in the semi-log plot two regions of interest. In the short time, you see the effect of the valve, so the time constant of the valve, while the long time asymptote offers essentially all the information on the mass transfer. The model has 4 parameters, delta and gamma, which are essentially depending only on the equilibrium, so they are not estimated, they are simply coming from the mass balance, so they are not fitted, while the only 2 parameters to match remain the valve and the mass transfer coefficient. So essentially, you match the initial zone, the initial region in the short time and the long time to get the full curve that matches the experimental data. What we call valve effect, obviously, is not just the kinetics of opening and closing the valve. It involves the whole conductance to the valve and the piping that connects the dosing to the uptake. This is calculated with the relationship that is displayed here, where on the first part of the right-hand side, you see essentially the average concentration across the section, and then the pressure difference between the dosing and the uptake, i.e. the driving force for the gas to flow. It's essentially the equation of a flow through a pipe. Why it's important is that to understand this relationship is that the valve constant for a volumetric system cannot be determined with a blank experiment, because during a blank and when you have instead the sample inside the active volume, the pressure would be lower in the case of when you have the adsorbent inside the sample cell. So obviously this one affects the dynamics and time constant of the valve as well. The other important consideration is that as you go up in pressure, the impact of the valve increases, and you become you can incur into essentially a situation where the system becomes progressively faster, and your response becomes essentially controlled by the valve response. So it's important to do also these checks and understanding how the system behaves in the whole pressure region. The reduced pressure plot has an extra advantage, is that it allows you immediately to determine, obviously, if you are in isothermal conditions, the difference between a surface barrier and a diffusion type of transport. So because what you have is that even though you have in this plot the same slope in the long time region, the intercept between the two models is very different. So this one essentially allows you to match, to understand when matching your models with your experimental data, to understand which of the two systems, transport models is actually controlling your system. And as I said, the difference between diffusion and surface barrier, it becomes is immediately clear if your system is isothermal. That's why you want to work under isothermal conditions for your kinetic measurements. Here is an example. So here you see also the configuration of our system. So this is again nitrogen in lithium LSX at minus 15 degrees. So we slow down the system in order to see clearly the kinetics. In the red box, in this red picture, what you see is the 2 sample masses that we used. So we used 2 sample masses, and also we used inert material like stainless steel beads to lower the thermal mass, to increase the thermal mass of the system, so bring it as close as possible to isothermal conditions. When matching the curves, the model with the experimental points, what you see is that immediately you see that the system is controlled by the diffusion model, in contrast with what the automated software of the machine, of the instrument I showed you before, was saying. So this one is clearly a diffusion model the slope of the surface barrier can be matched, but the intercept does not match with the experimental data. Obviously, we did also all the checks for isothermality and linearity by running the adsorption-desorption. And as you can see, we changed the sample mass. And as I mentioned, also, we used the stainless steel beads to bring the system as isothermal as possible. Another case of, so what we discussed just now was a fast system, so 44 seconds for the diffusion time for the system. We now move to a slow system. So this is carbon molecular sieve with the prop molecule of essentially CO2. We try different pressure ranges. We try the temperature at -5 degrees. And in order to keep the system as isothermal as possible, we essentially manufacture custom-made copper holders where the individual pellets are placed in order to essentially isolate it from the rest of the bed. So essentially what you have is that each individual bead is surrounded by copper. This allows fast transfer of any heat generated during the adsorption, and allows us to run the system as close as possible to isothermal conditions. Obviously, for each of the equilibrium tests, the kinetics test, we also run absorption and desorption. And as you see, we also change the configuration of the sample. What you obtain is the curve that you see here. So now you see the time scale is much longer. The curve goes on and continue going for 300 seconds and longer. So it's definitely a slow system. What is important to notice here, obviously, by our analysis, we found out it was a distribution of surface barriers. What is important to notice in this plot here is that obviously the system is slow, so the effect of the valve is practically negligible. You could go away with a simple model where you assume the valve is infinitely fast. But what I want to show here is the advantage of actually plotting the reduced pressure instead of the transient uptake, because the fractional uptake. Because in the fractional uptake, your plot goes from 0 to 1, and all the information that you see here, which is very well highlighted in the long time region, will be lost in the approach to the plateau. So you won't be able probably to see the effects of the multiple surface barriers that you see instead by plotting using the reduced pressure. Bed effects. Okay, so that's a system, that's a complication that you can have in a volumetric and gravimetric system. The best way that I find to explain how bed effects can be understood is by going through very quickly the understanding of macropore diffusion, because as you will see, from the gas point of view is not different from a macropore controlled system. In a macropore diffusion system, so what you have is, for example, a pellet where you have your macropore solids, so your crystals, embedded into a binder, and you have a network of essentially macropores that connects different crystals and a binder that keeps everything together. The definition of the effective macropore diffusivity is essentially the one reported here, where you have the total for diffusion that includes, depending on the technique, the molecular, the Knudsen, or the surface diffusion. And then in the denominator, what you see is the local slope of the isotherm, so the equilibrium parameter. The general assumption is that what we see very often is that people tend to assume that because the micropores are way smaller than the macropores, the system should be macropore diffusion controlled. The mistake in this approach is that what you should really compare is the diffusion time. So the radius squared of your particle of reference divided by the diffusion. If you do this analysis, you will see that when you compare the diffusion times, in the case of a pellet, so a macropore diffusion system, the radius of a pellet is on the order of millimeters. In the case of a crystal, now you're going microns or sub-microns. So there is already 6 orders of magnitude in the diffusion time, because obviously it goes with the square. And if you add also the fact that the macropore diffusivity has essentially the equilibrium constant in the denominator, this one can go for 2 orders to 6 orders of magnitude. So now you see that essentially, if you compare the diffusion times, unless you are in the case where the size of the molecule is very, very close to the size of the micropores, you're very likely to be controlled by macropore diffusion. Now, how the bed effect happens and how it relates to the macropore diffusivity. When you work with powders, for example, powder especially below micron sizes, they have a tendency of agglomerate. So here I took a picture of some powders that we have in the lab. On the left, what you can see is that the powder that are supposed to be individual crystal tend to agglomerate into particulates of dimensions that are very similar to the dimension that you see on the right, which are essentially commercial beads. So from the gas point of view, even though there is no binder, you're essentially traveling through a network of macropores. In this case, the macropore is the space between the crystals. So this case is no different from the case of a macropore diffusion control. So what is important is to make sure that you change the configuration of the sample and disperse, in the case of powders, the sample in a rock wool or in a glass wool across your sample cell, or as we do, individualize and put in the samples in different compartments of your haptic cell in order to deal essentially with single particles. Study on bed effects were done already in the 80s by Ruthven and Lee. Here I report one of their papers from 1981 is essentially measuring octane in 13x crystals. And you will see that here I list a lot of the stuff I've been saying during this presentation, a lot of the recommendation. They use very small amount of sample. They use the same sample mass, but they change the crystal size. A really important check if you have the possibility of changing the crystal size. And they also look at different pressure steps. What you see on the plot on the right is that is a proof of bed effect. The crystal agglomerates behave like a bead. Changing the crystal size doesn't change the response. So obviously here, what I'm highlighting is that things can be done in order for you to check if you have bed effects or not. Distribution of the sample, changing the crystal size if you can, changing the sample mass, i.e. the size of the bed, essentially will help as well. So do a few checks in order to make sure that what you're measuring is effectively the diffusion inside the pores and not the external contribution of the transport. Finally, I'm moving into the presence of heat effects. This, as I said, is something that is very important, especially for systems that are not in flow, as is very often the case for balances and volumetric systems. I'm reporting here some of the works that Professor Ruthven did in the 80s, where he looked essentially at the thermal effects. At the time, he was working with the gravimetric system, so he was looking actually at the thermal effects in gravimetric system, and he also studied, as I reported before, the combined effect of non-isothermality and also bed diffusion in beds. So these are some of the papers where essentially he put together some important observation regarding the thermal effects. First one is that very often the non-isothermal response cannot be distinguished by the isothermal one. So the two responses, they often look very similar in shape. Hence, the goodness of fit is not as always a good indicator of the physical mechanism of what is happening inside your system. Another observation is that try always to use the smallest possible quantity of sample, and in order to minimize the effects of thermal effects, dispersion of the sample and using an inner material in order to increase essentially the transfer area of your system. He also comes up and define a criterion for isothermal behavior, which is what you will see in the next slides, what we use and what we call as Rømer number. So alpha divided by beta, according to his notation, higher than 60. Here, essentially, there are some key considerations regarding thermal effects. Any adsorption is associated with a temperature increase, regardless of the pressure step. As you see in the relationship there is no pressure included in the equation there. So obviously, it's independent of the pressure step. The temperature increase will always be essentially associated with adsorption. The parameter, the Ruthven number are the two parameters alpha H and alpha equilibrium that are defined here. The first one is the ratio of the diffusion time and the heat transfer. So obviously, we can try to increase this parameter by to mitigate the heat effects, but obviously by changing essentially the thermal mass of the system. But for fast system, i.e. when the diffusivity is really high, this is always a problem. So thermal effects are very prone for system, very likely in systems that are fast. The other term, alpha equilibrium, instead has essentially a proportionality with the square of the heat of adsorption. So strongly adsorbed component, which are also fast, may lead to completely limited system. The general criterion is that the higher the Ruthven number, the more likely you are to be in isothermal condition. Another important consideration is to see what is the pressure dependence of the Ruthven numbers, i.e. what happens to our thermal effects when we go up in pressure, as essentially the techniques are described. As you go up, as you essentially measure the kinetics, the standard experiment will lead you to have different pressure steps. If you're measuring isotherm, you want to look essentially at the transient of each pressure steps. So what happens when you go up in pressure? You can define, for the case of a Langmuir isotherm, a non-linearity parameter. This parameter essentially goes to 0 the further away you are from the saturation, and close to 1 when you're approaching essentially saturation. You can do the cases for the micropore diffusion and the macropore diffusion and see how the Ruthven number essentially depends on the nonlinear parameter. What you see here is that the heat effects are always going worse. As you can see, the lambda is on the denominator as you go up in pressure. This is always the case for the micropore diffusion and the macropore diffusion control. The additional thing that you see is that macropore diffusion control system will have a stronger effect because they have the equilibrium constant in the denominator, and is also depicted here in the relationship with the dependency essentially of the Ruthven number with the nonlinear term. So obviously, the recommendation here is start always at the lowest pressure that you can, and then progressively go up in smaller step until you can see, if you see, essentially the heat effects. Example, this is our data from our lab. This is lithium LSX measured in our ADVA system. We are dealing here with 4 binderless beads. 4 milligrams each for each beads, and as you can see, we use our copper holder where we isolate the 4 beads into the copper holder, so each bead is isolated, surrounded by copper. We use very small pressure step of 2.2 kilopascal, and we looked at the range of temperature that goes from -10 to 30 degrees, and essentially to look at the different temperatures, and we look at adsorption and desorption for small sample essentially dispersed inside the bed. What you see on the left here is we look at the first lowest pressure point. The response is completely isothermal, going from -10 to 30 degrees. 30 degrees, I would like you to see the time scale. We are looking about 2 seconds for the response of the 30 degrees example. And the information on the kinetics is only on the 1% of the signal. On the plot on the right, what you see is the different pressure steps. So as you go from 1 kilopascal to 55 kilopascal, you move essentially from an isothermal system to a combined system with heat and diffusion, and then finally 55 kilopascal, you are completely heat limited. So even applying all the recommendations, the small sample mass, the small pressure step, and so on, and the slowest system that we could achieve with this sample and this adsorbate, we still have heat effects. So not always you are able to actually eliminate the thermal effects. In the table here, there is essentially an accounting of all the tests and the Ruthven number. You can see as you go up in the pressure, the Ruthven number decreases dramatically from the hundreds to hundreds to 2 or 3 as you go up in pressure. Another information on the plot on the right is we try different configuration with the copper holders and without the copper holders, with the beads dispersed in stainless steel beads. And as you can see, as you go up in pressure, you see the effect of the change in thermal mass that makes the system with the stainless steel beads more non-isothermal. Finally, we are moving into more interesting materials, more 3D printed monoliths and stuff that essentially require more refined techniques to actually determine the kinetics of the system. So on the left, you see experiments done again on our differential system on a whole monolith of 13x. It's completely surrounded by metal beads to make it as isothermal as possible. On the right are the fragments from the same monolith tested again individually on the copper holder with a very different sample mass. We go from 1.6 gram, obviously, for the whole monolith to a few 35 milligrams for the single pellet, for the single fragments. What's the main issue? On the monolith, essentially, you are forced to go to the lowest pressure possible. So here we're talking about 0.16 torr in order to have an isothermal response. Going up in pressure will essentially lead to inevitably to a non-isothermal response. On the fragments, obviously we see the isothermal response on the slowest pressure, on the lower pressure, and then as we go up, we move towards more contributions of the heat effects until we reach the case of a purely heat-limited case, where essentially changing the diffusivity will not make any difference in the response of the system, of the model. We present in our review also a workflow of experiments, which I think is very useful for anybody who's approaching the use of essentially volumetric and gravimetric system for the measurements of mass transfer kinetics. Essentially, there are all the checks, all the steps to follow, the consistency check, the adsorption-desorption step, check for the for linearity across the step, for heat effects, change of configuration of the sample, and so on. Essentially, this one leads you, if you follow the arrows and the blocks, will lead you to the model that you need to use to analyze your data. If you assume an isothermal model, the simplest model possible, and all your assumptions are met by the experimental checks, then obviously you should analyze your data with your simplest model and all the assumptions are checked. But if not, then you should go back, either change the configuration of your system and bring it to in order to achieve the assumption that you made, or essentially move to a model that accounts for the complexity of the system, so heat effects, bed effects, and so on. Finally, I will conclude with a summary of the IUPAC recommendation, which I have essentially listed at the beginning, went through the presentation, and here I report directly what is in the report that we published. At the very end, you will find a series of tables, each for each experiment. So this one is the one concerning the gravimetric and volumetric, so the uptake measurements. And I highlighted here the wording that we use in the paper and what it actually corresponds in terms of practical terms. Using the small amount sample possible, change the sample configuration, so disperse, isolate, and changing the bed configuration, use the rock wool and so on to check for bed effects. Add or remove inert material to verify that the system is isothermal, and trying to change the configuration as well to make sure that the system is as isothermal as possible. Vary the concentration step. You want to stay as limited as possible with the pressure step, the concentration step, and you want to verify if changing the concentration step will allow you still to be in linear condition. Run the adsorption and desorption, very simple check, in the same pressure step that you are considering for your kinetic experiment. One additional information that is reported here. In the principle of measurement, we say determination of the intrinsic diffusion time. So what we measure is the diffusion time. So this one is what should be reported. This is very important because reporting the diffusivity very often is not enough to understand what is being, so if the system has actually been used to measure the diffusion inside the particle or is being essentially compromised by other effects. An example in the slide that follows, look in the papers that you read for the diffusion time. So here you see, I won't go into the details of the discussion that the authors made on the hyperloop-like diffusion. What they report here is the experimental curves converted, the experimental signals, and the model, and they report the diffusivity. If you now convert using essentially the size of the particles of the crystals that they use, this diffusivity into diffusion times, what you get is that the diffusion times that they measure, according to the diffusivity reported, are on the order of fractions of milliseconds, 0.1, 0.02, 0.01. So clearly, once you see the diffusivity in terms of the diffusion time, you can see that there is no macroscopic technique that can measure these diffusion times. So obviously, this is an indication that should be very worried about using time constants, so diffusion times that actually have no relationship with the actual diffusion inside the solid. With this one, I conclude my talk. I would like to thank the organizer of the webinar and the audience for their patience, and I welcome questions.
Thank you very much, Enzo. Excellent talk. We have one question on YouTube at the moment from Arvind Rajendran, and he says, thank you for your talk. And the question is about challenges of measuring kinetics of humid systems. And so do you have any recommendations for that in gravimetric systems? Are there any limitations on time constants you can reliably measure, and so on?
All right, so obviously in the case of the humid system, you're meaning only a single component, right?
I think it would be useful if you could address both cases. So say water in non-adsorbing component and a binary system.
Obviously, for water systems are generally slow systems, so you should be able to, especially if you have a flow through balance, for example, which is like the main technique. Again, the recommendations are equally valid for the case of water. So the recommendation I made, first of all, check the raw signal, how quickly the signal, your relative humidity goes to the new pressure steps. And if the pressure step is a lot faster than the transient that you see on your balance, then obviously you have enough information to actually extract the kinetics from the system. The moment you move into co-adsorption of multiple gases, obviously the system becomes a lot more complicated to analyze. Again, the same recommendation apply, but you want to make sure that in this case, the equilibration of the mixture to the new set point would be a lot slower because of the diffusivity, the molecular diffusion in the gas phase. So you need to first make sure that the system is equilibrated in the gas phase, and then essentially look at the kinetics into the adsorb phase.
Great, thank you very much. I think what you mentioned in that answer for the gravimetric systems and the time constant, also what you mentioned earlier in your presentation, follows on pretty well to this question. Do you have any such recommendations for volumetric systems, or should someone just use the reduced pressure plot in those cases to identify too fast, too slow diffusion in the system?
The reduced pressure plot is clearly the easiest way. It allows you to check if you actually see the response. So if you plot your experimental data before putting the model on top, if you plot them converted into reduced pressure, you will see, like in the slide where I show the model, that you see an initial decay, which is normally the time that requires the valve to open and the gas to flow through, and then the time constant of your system. If you see the two, if you can distinguish the two, then it means that you have a contribution of the valve in the very few, I don't know, 1 second, a fraction of a second in the fast system. What you want to make sure is that you see the tail of your time constant, which is very different from the kinetics of the valve to flow through the valve. Okay, so this one allows you simply to inspect the experimental data and see which one, if you actually are in a situation where essentially are completely controlled by the valve. You'll be in such situation only when you are either dealing with the system which is very, very fast, you're going up in pressure, so you are completely controlled by the valve, and in the case you try to slow down the kinetics of absorption by, for example, going down in temperature and making it slower than the resistance to the flow.
Great, thank you very much for the detailed answer. We have another question coming through on YouTube. One of the viewers is having trouble measuring CO2 on, I assume, molecular sieve and not carbon molecular sieve, at 1 ppm concentration at pressures in the 1 to 2 bar range. Do you have any recommendations for this scenario?
Well, clearly the user is using a good approach by using a small concentration. It may be wise to try different concentrations. Because I don't know the limitation, I don't know which technique they're using. I assuming it's a flow through balance at this point. So it may be that the concentration is too small to actually be seen. You only see essentially a very noisy signal to actually extract the kinetics. So it may be worth trying different concentration and then progressively reduce it to check what is the limit, so the noise to signal ratio that allows you to see clearly that the dynamics essentially.
Thank you very much. I hope that was useful to the viewer. We have another question kind of relating or whether it is possible to relate the diffusion of one species on a given solvent to another, and whether that is possible. But I think that would just depend on your diffusion model used and which controlling regime you are in and so on. Do you have any comments on that one?
Well, if you are, for example, in I don't know, in macropore diffusion, where you essentially are controlled completely by Knudsen diffusion, you can somehow predict what's the contribution depending on changing the molecule, but I think it's a bit. I'm not sure I understand the question itself. If you can actually predict on the same adsorbent, I guess, what would be the diffusivity of a different gas?
Yeah, I believe that's the question.
So there may be, if you know, for example, if you are under macropore diffusion control, knowing the isotherm will allow you to have an estimate of the difference, at least, of the ratio between the diffusion time between one and the other one.
Great, thank you very much. And one final question, just to wrap up, related to the ADVA system. Is there any, or how tight does the tolerance have to be in the two volumes on both sides for the reference and the
We
sample?
don't assume the two volumes to be the same.
Okay, so you can model that
So
later on.
the volumes
Right.
are very similar in terms of, I don't know, 10.4 whereas 10.5 or the second digit in CC, for example.
Right.
So they are very similar, but we never assume in our models and in our calculation that the volumes or the temperature are the same. So we have sensors for temperature. We have calibrated individually all the volumes of the system. So there is no assumption made there.
Great, thank you. And does
We
that
keep
also
it
include
symmetric and similar for the purpose of actually increasing the resolution of the system, but we never assume they are the same.
Right, thank you. And does that also include a sample volume subtraction on the sample side?
Yes, so we measure the sample volume and we make sure that the reference side has the same amount of volume. So we put inert material on the samples on the reference side to replicate the volume of the sample we are using on the uptake side.
Great, thank you very much. With that, I think that's all the questions that have come through. So I'd like to thank you again for the very excellent presentation. And I'll now pass over to Nick, who will wrap up the session for today.
Thank you, Dr. Enzo Mangano, for your presentation using volumetric and gravimetric techniques for the measurement of mass transport kinetics in porous materials. For our special IAS webinar series, Diffusion in Nanoporous Materials, Guidelines for Measurement and Reporting, focusing on the recent IUPAC titled Diffusion in Nanoporous Materials with Special Consideration of the Measurement of Determining Parameters. We also thank all of our attendees for joining this webinar and hope that it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili. The hope is that the work discussed today will be a useful resource for the absorption science community in the future. The next confirmed IAS webinar will be given 1 week from today by Dr. Stefano Brandani on April 16th at 1400 UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed, LinkedIn page, and through the IAS mailing list. With that, we thank you for joining and hope that you'll join us again soon.